Chapter 8, Section 6 is about something called vectors. So by the end of this lesson, you should be able to find the magnitude and direction of a vector, and then use vectors and vector addition to solve real problems. So what is a vector? The speed and direction of an object can be represented by a vector. A vector is a quantity that has both a length and a direction. You can think of a vector as a directed line segment. The vector below may be named AB or V. Now I know this kind of looks like a ray, but remember, if you have a ray, it goes on forever and ever. So it starts at a point, and then that arrow literally means it goes on forever. When we write a ray, we would write this like A and then B. We would write it with an arrow over top of it. These vectors, if you look, it's like somebody cut part of the arrow off. It's a V with a half arrow, showing that it actually ends at this point, the terminal point. So a vector can be named using a component form. The component is an X and a Y, and it kind of looks like a coordinate point, except instead of parentheses, we have almost like the greater than and less than symbols there. But it lists the horizontal and vertical change from the initial point to the terminal point. And that's important. It starts at the initial point and goes to the terminal point. So when you look at this vector that they give us here, when we write the component form, we're going to start here and then talk about how to get here. So you always move in the X direction first. We got to go over 2, and then we had to go up 3. So that's why the coordinate is 2, 3. So write this vector in component form. So remember, we have to start here and somehow get to G up there. So you always move with your X first. So we had to go back 3, so it's got to be negative. And then we have to go up 1, 2, 3, 4, 5, so it's positive 5. This vector right here is very different than positive 3, 5. If you were to list positive 3, 5, you would have to go in this direction 3 and then up 5, so that would be the vector, which is very different than the one that they gave you. So be careful that you pay attention to your negatives and always do the X part first. So write this vector in component form. So wherever this point is at -8, 1, M will be here, N is 2, -7. And this is important that you look at this. You notice that you start at M and go to N. So we got to list how to get from one to the next with our X's. If you notice, I didn't make little slashes here because it doesn't really matter. You can use these points. So if you're going to start at X is -8 and go to +2, you have to move in the X direction 10 spaces. So you're basically finding what's the distance between those two numbers. And then same thing with the Y's. If you start at 1 and go down to -7, I have to subtract 8 to get there. So this is the component form of that vector. So another vocab word, the magnitude of a vector is its length. The magnitude of a vector is written AB with absolute value bars around it. When a vector is used to represent speed, the magnitude of the vector is the speed. So if something was traveling like this versus like this guy is much slower because it's shorter. So for example, if a vector represents a course a kayaker paddles, the magnitude of the vector, or the length of it, tells you the speed. So draw the vector -1, 5 on the coordinate plane. Find its magnitude to the nearest tenth. So if you're just ever told to draw this, start at 0, 0. And it doesn't really matter where you start, but 0, 0 is a good spot to start. And then this told me to move -1 on the X and then up 5 on the Y. So that's how we drew this vector. I want to find its magnitude, which means I want to know how long this part is. Using what we know about right triangles, we can create one here. This right here is a nice pretty right triangle. Know this length down here is 1, and that length is 5. So we're going to do a² + b² = c². So my A is 1, my B is 5. That equals the length that I'm trying to find, C up here. So you get 1 plus 25. And if you add that up and take the square root, you end up taking the square root of 26, which is about 5.1. Whenever you are asked to find the length, it is always the square of both of those numbers added together, and then you take the square root every single time. So another word you need to know, the direction. So the direction of a vector is the angle that it makes with a horizontal line. This angle is measured counterclockwise from the positive x-axis. So when you start here, this is like 0 degrees. As you go around, this would be 180, and then you can keep on going, like this would be 270. And then it eventually ends up back at 360. So this angle right here, if this is my horizontal line, is 60 degrees off of the horizontal. Sometimes the direction is given in reference to a compass, like never eat soggy waffles kind of a deal. So when you have the directions north, east, south, and west, pay attention to how they tell you what the direction is. So when you're given something like this, it's saying you're looking north, and then you go 30 degrees in the east direction. So you start looking north, you go 30 degrees in the east direction. So if I gave you south 30 degrees east, it would be you're looking in the south direction, you go 30 degrees towards east. So the force exerted by a skier is given by the vector 1, 4. Draw the vector on a coordinate plane. So just like before, we're going to start at 0, 0. 1, 4 tells us you're going to move over 1 and up 4, and that's how we came to that point there. Find the direction of the vector to the nearest degree. So what we're looking for this time is this angle right here. We don't know it, but we can make a triangle. So just like I had erased here, this is a nice pretty right triangle, and we need to find this angle right here. So if we draw this a little bigger so we can see it, this is the angle we're looking for. I know to get to this you had to go out 1 and up 4. So then we're going to use one of our inverse trig functions. Since the two sides I have relative to this are the opposite and the adjacent, I'm going to use tangent. So tangent of the angle I want is the opposite divided by the adjacent. So then I end up doing inverse tangent of 4. And if you type that into your calculator, you get 75.96, or about 76 degrees. And stop and make sure that makes sense. Remember, straight up like this would be 90 degrees. This is pretty darn close to that, so it makes sense that it's a big angle like 76 degrees. So next up, we have two more vocab words, equal and parallel vectors. Two vectors are equal if they have the same magnitude and same direction. Remember, this means length, and this means degree. So when you're looking at something like this, if you basically draw yourself a nice little triangle, you're asking, are these triangles similar? Like, will I get the same hypotenuse? And in this case, I go up 2 over 4, up 2 over 4, and they are the same length. Equal vectors do not have to have the same initial point or the same terminal point. They're just next to each other. Two vectors are parallel if they have the same direction or if they have opposite directions, and they may even have different magnitudes. So for example, these ones go in opposite directions. This guy's little, this guy's big, but if I was to find their slope, down 1 over 2, down 2 over 4, they simplify to the same number, -1/2. So that means that they're parallel. So you're going to get some problems like this, where it says identify equal vectors. Now remember, they have to be going in the same direction, and they have to have the same magnitude. So automatically we know this, KL, doesn't have any equal vectors because all the other ones are pointing up. Now, when you just look at these two, this guy is a little more slanted. And we can prove this with math. If I was to make a triangle with those two here, this side would be 3, this side would be 1. If I was to do Pythagorean theorem and figure out what this is, it would be exactly the same. And then we can look at it as our slope as well, down 3 over 1. So JI, or IJ, and OP are equal vectors. And then these are also parallel. The other thing to look at when you're looking at parallel is remember they don't always have to go in the same direction. So if we take a look at that one that we have here, these two would have the same slope. Down 3 over 3 is exactly the same as down 2 over 2. So let's write some parallel lines in here. But then we also know KL is parallel to MN. All right, last little bit of this. The resultant vector is the vector represented by the sum of two given vectors. To add two vectors geometrically, you can use two things, the head-to-tail method or the parallelogram method, and I'll show you those in a sec. To add vectors numerically, you just add their components. So if you're given components, all you got to do is add the x from this one and this one together. That's your new one. And then add the y's. That's your new one. So if you're looking at it geometrically, like if you actually pick up the vectors and move them, head to tail method, you place the initial point on the second vector on the terminal point of the first vector. So this red one's our first vector here. It's going in this direction. And then we're given another vector. So we place the tail and the head next to each other. And then this green one here is the resultant. So if you have somebody moving in this direction here and then like the current or the wind pushing them in this direction, they're really moving in this direction here. That's the resultant. The other thing you can do is create a parallelogram. So forget that this green one's here for a second. If these are your two vectors, you redraw this one here and redraw the other one over here, and then you know that the resultant vector is right in between. So let's do a problem, and we'll do plenty more of these in class. An airplane is flying at a constant speed of 400 miles an hour at a bearing north 70 degrees east. So if we were to draw this, north 70 degrees east would mean that we were going north and then we went 70 degrees east. And this is 400 miles an hour, so this is our plane. And then it says a 60 mile an hour wind is blowing due north. So this is the wind. It's blowing directly north. Now if we were to use the head to tail method, we would definitely need some graph paper to make sure that this is consistently true, but you can kind of get an idea of where this is going. The plane's going in this direction, the wind's pushing it in this direction. So we know that when we get done with this, the plane is really going to be going somewhere here. It's not going to be going at 70 degrees, it's going to be going a little less, and it's going to be traveling a little faster than 400. So what we need to do is find what that red vector is. So in order to do that, let's take a look at just the plane part. So I'll erase these. We can figure out the component of both of these. So that's what we're going to do. Find components. So if we look at the plane, that means I want to know how far I moved on the x direction and how far I moved in the y direction. Now the only information I have is basically the hypotenuse here if we create a nice pretty triangle. If this is 70 degrees here, I know that this whole thing has to add up to 90. So the little sliver in my triangle has to be 20. And then we got to find the y and the x. So let's use one of our trig functions. So let's find x first. Because the x is the adjacent side and we have the hypotenuse, I'm going to take the cosine of 20. That equals x over 400. So I end up with 400 times the cosine of 20, and if you type that in your calculator, you get about 375.9. So that is this right here, 379.5. And then I'm going to do the same thing to find the y, except this time I'm going to use opposite over hypotenuse, so I'm going to use the sign. So y over 400. If you plug that into your calculator, you get about 136.8. So that's what this is here, 136.8. So now I know my component for the plane. I go over 375.9 and I go up 136.8. Now the wind is way easier. Because it is due north, I'm not going to go any in the x direction, and I'm going to go up 60 in the y direction. Now remember, in order to add things geometrically, we need some graph paper. We don't have any, so we're going to add things algebraically. And remember, all we have to do is add the x and the y's up. So, combined, our new direction is 375.9, because we added this and this. And then in the y direction, we got to add this and this. So you end up with 196.8. So again, if we were to draw that, we would go over 375.9, up 196.8, and our vector would be somewhere here-ish. But now I'm asked to find what the plane's actual speed is and direction. So I need to figure out this guy. Oops. I know what these two lengths are because that is my component. So what I'm going to do in order to find c squared is take these two things and square them and then add them together. So 375.9 squared plus 196.8 squared, and then take the square root of that. So I end up with c being 424.3. So this means the plane is actually going 424.3 miles per hour. So the wind's helping it. Remember, without the wind, it was going about 400. But the wind is also pushing it. So originally it was going 70 degrees north, 70 degrees east of north. We got to figure out what this new angle is right here. So again, in order to do that, we can use our trig functions. We're trying to find this angle. We know the y is 196.8 and the x is 375.9. So I'm going to use tangent. Tangent on my angle is opposite over adjacent. And when you do the inverse tangent of that, let's see, 196.8 divided by 375.9, you end up with about 28 degrees. Now remember, that's 28 degrees right here. So if we want to put it into how we had this right here, we need to know what 28 minus 90 is. And that means this angle right here is about 62 degrees. So our plane with the wind is going 424.3 miles per hour at a direction of north 62 degrees east. So there's a ton of work with just this one problem, but we'll do more in class so you can ask questions and get some practice. So finally, this is it. You should be able to find the magnitude and direction of a vector. That stuff should be a little easier. And then use vectors and vector addition to solve real problems. That's what we just did. So if you have any questions, make sure you write them down and we can go over them in class. Enjoy your night.